Hello everyone. So in this video, what we are going to discuss on the board again is basically the concept of inheritance of a metric. And in fact, the point here is that depending on how you define a curve, so we are going to focus on the metric that is inherited, sometimes people say induced, on a particular curve. Um, and we are going to see that this is something important, like a notion that is important to appreciate if we want to understand, in fact, the freedom that we may have if this inheritance property was not used. Okay, so basically that's it, and let's go. Right, so let's start first by saying that we want to define a curve, okay? And it turns out that with modern geometry and including differential geometry, people have realized that there are plenty of ways to define curves, surfaces, and so on. But I'm going to focus on curves for now. Um, Now, in general, in differential geometry, you would define a curve in a quite strange way. Essentially, you would, first of all, let me check one thing. Yeah, okay, the sounds seem to be there. So one of the things you would do is you've got two choices in differential geometry, and the tools that have been developed, essentially more modern tools, correspond to what are called inherent or intrinsic characterization of the curves you want to define. And the way it works is basically you need to have a set of preconditions to build progressively the structure of the curve you want to characterize. And so you need to start first with a topological space. So essentially, that's a set that you endow with a structure of so-called open sets, open subsets that have some properties. And once you can do that, you have a topological space that allows you to define notions of neighborhood and so on. Okay, so you need to have a topological space. That's what you start from, and then you need to be able to say that this topological space is homeomorphic. So that means that there is a bijective function, so-called diffeomorphism, that from the topological space you are in to subsets of the reals. Okay, and once you have that, you have what is called a one-dimensional manifold. Um, Now the thing is that once you've got this one-dimensional manifold, that's not finished. You need to basically add structure to it. So often you are going to add some, like, the notion that you can define, and you may define differentiable functions directly on the manifold, and then in which case people say or talk about a differentiable manifold. And then you may define some so-called linear structures that are basically at every point, and these linear structures are called tangent spaces. And these tangent spaces enable one to define fields in various shapes and forms. And the totality of them in your space is called the tangent bundle. And then once you've got that, then you need to then start saying, okay, what happened then if I try to differentiate or take the gradient of a field and stuff like that? And when you start thinking about this stuff, then you realize that you need a way to connect the fields from the same field, if you will, from two different tangent spaces. And the way you do that is via what is called a connection. And the connection, for those of you who have some knowledge of differential geometry, is given by something called Christoffel symbols. Now, the connection in principle is separated from the concept of metric, so from the geometry of your manifold, so of your curve. However, it turns out that, for example, often people would use what is called the Levi-Civita connection, and the Levi-Civita connection actually gives a relationship between the metric and the Christoffel symbols. So the bottom line is that you see that you can have an actual topological space that you can describe, you can have tons of features for it, and yet not even talk about yet geometry and metric and so on. Okay, so metric is often something that is added kind of one of the last items to be added to your overall kind of manifold and curves and so on. Okay, so at least as far as we are in 1D curves. So you see, it's a very, very intricate and complex thing to do, and more than that, actually, these steps are, in a sense, arbitrary. So they are up to you to define whatever metric you want on the curve you've designed and so on. Okay, so that's why many people can talk, for example, about a flat torus. So a torus, we do have this idea of a donut shape. So here I'm talking about two-dimensional manifold, but it's just to give an illustration. But then you can also think of a flat torus where the metric would be completely flat and Euclidean, but the topology would be that of a torus. Okay, so so that's why we need to be careful not to conflate the very general notion of a torus in this kind of topological sense, which often stems from the intrinsic or inherent way of characterizing the surface or curve and so on. Um, while what we are used to, and that's the intuition we derive from, is basically the embedding strategy. And so the embedding strategy, when it comes to a curve, is much more straightforward, at least much more intuitive to us. And it doesn't give, in a sense, any freedom on what happens. And in a sense, it gives us a sense of security, if you will. And so what happens is that you embed your curve in R2. Okay, so usually in R2, but when you use embedding strategies in general, you take the smallest linear kind of Cartesian space within which you can embed your system. And then when I say R2, usually what is implied is that R2 is itself endowed with the Euclidean metric. And what we call Euclidean metric in traditional kind of algebra is basically a metric which is satisfying Pythagoras theorem. Okay, so if you have a triangle with a right triangle with basically these two sides that are dx and dy, then the length of the hypotenuse is going to be the square root of dx squared plus dy squared. Okay, so that's what the Euclidean metric actually means. Now, the question that people ask then is, if I have this Euclidean metric, so again in R2, when I've got arbitrary dx and arbitrary dy, for example, then the question is, what is then the metric that is inherited on a curve gamma if this curve gamma is defined by some function of x and y that is equal to a constant. That's the definition of a curve. When you are embedded in R2, the curve is defined by a relationship between x and y that is in general phrased as f of xy is equal to some constant. Okay? And then basically what happens is that the curve is going to inherit a geometry, essentially a way of measuring length from the embedding space, which is R2, with the Euclidean metric. Okay, so that's basically what happens. And so what I want to do here is simply remind you or tell you how we actually derive this inherited metric on the curve and see how that goes. So the first example that comes to mind, and that is quite straightforward and very common, is basically if we take f of xy is equal to r squared. Okay, and then and I said that in fact, sorry, let me rephrase that a bit. So I've got f of xy is x squared plus y squared, and that's equal to r squared. Okay, so I can imagine something like this. You all got that this was the equation of a circle, and what I want to know is essentially what is the inherited metric, so the arc length basically. How do I calculate that, given that I know that the Euclidean metric applies in R2 within which the circle is embedded? Okay, and so the way you do that is you simply there are multiple ways to do it, and here I'm going to show two of them. You So first of all, we do start from the so I'm going to write ds gamma. That's going to be the Euclidean metric directly. So that's going to be, so let's say the square of it for now. So it's going to be dx squared plus dy squared, but here I need to specify in some shape or form that these guys belong to gamma. So I'm going to write here the gamma as well. Okay, so what that means is that x and y again are kind of connected together in some way. Now, there are two ways I would like to to show it. The first one is to take a portion, is to invert that equation for y, and then basically take one of the portions, and in fact the outcome is going to be independent of it. So so first option, the first option would be something like this. So I've got I say that y is going to be equal to plus or minus square root of r squared minus x squared. Okay, the plus is going to correspond to the upper circle semicircle, and then the minus corresponds to the lower semicircle. Now, once I've got this first option, then what I can do is I say, okay, well then dy is equal to, so that's going to be the derivative of this quantity with respect to x, and that's it, and then times dx. So I'm going to have minus plus, and here I'm going to have x, and then divided by r squared minus x squared, and then dx. So if I put everything together in this thing, I'm going to have the following. So ds gamma is going to be squared, is going to be equal to dx gamma squared. So here this is gamma. And then I've got plus dy squared. So I need to square that stuff. So I'm going to have x squared divided by r squared minus x squared, and then dx gamma squared. Okay? So in the end, I can basically write that ds gamma, if I want to express it as a function of dx only, I'm going to get the inherited or induced metric on the circle as being dx gamma. So again, and here in fact, that's any dx you want, but it's just to say that it's attached to this kind of curve, and then 1 plus, and in fact, let me go slightly, yeah, so that would be 1 plus x squared r squared minus x squared, and then I can actually, directly calculate 1 plus that, and I'm going to get a simplification where I've got dx, so let's tick yet for that, so that's dx squared gamma, and then I've got r squared, and then r squared minus x squared. Okay, now I can basically write therefore that ds gamma is going to be equal to dx gamma, and then the square root, so r divided by the square root of r squared minus x squared. Again, here I write dx gamma, but that's simply dx at that stage. It's just the the dx along the x-axis period. But at some point, I had to show here that somehow one of them is going to, like, these two guys are kind of tied together. Okay, so that's one way you could do it. If you want then to calculate the length of an arc length that goes from one particular x value to another, you could actually use that. Okay, so that's a perfectly fine kind of outcome, and that's the metric inherited on the circle by doing this. Now, of course, you may also be troubled because there is this r squared minus x squared there, and one of the things you can try to simplify things is to say, well, what if I find a change of coordinates such that r squared minus x squared turns out to be proportional to r squared? Then I can get maybe some consolation here or something along these lines. Okay, I won't get any consolation, but well, no, I can get actually some consolation there. So, of course, some of you may know that what you would get is basically, at least a possible solution, is x is equal to r cosine theta. Okay, note by the way that I could choose, and maybe I will do that just for the sake of it, and I will do that actually for the sake of it. I will change kind of things, you can choose x to be, for example, r sine theta. Okay, these things don't matter. So here I'm simply choosing a coordinate system such that r squared minus x squared is going to be proportional to r. So let's say I'm using this. So then I'm going to get dx is equal to r cosine theta. Okay, so that's the dx that is going to go here. And then if I write ds gamma, I'm going to get here. So I'm going to get r, and then I need to differentiate the cosine, sorry, x is equal, and then here d theta. Okay, theta is my new variable. And by the way, the fact that theta on its own is characterizing the curve, and in fact x here as well, is obviously in line with this idea that your curve has to be so-called homomorphic to a subset of R only, okay, and not R2. So that's what we are doing here. So that being said, you basically write dx here, so you've got R cosine theta d theta. And then here you've got the r, so basically that would be r squared. And then divided by, you've got r squared, and then minus r squared sine squared theta. And then you've got the square root of this. Okay? Now, r squared minus r squared sine theta, you know that 1 minus sine squared is cosine squared. And so what you're going to get is r squared cosine theta d theta. By the way, this is I need to be a bit careful here because I do have sine theta. I think I should have done this at the level of ds squared, because what I'm going to get here, I'm going to get obviously r, but then what I get in principle is the absolute value of cosine theta. Okay, because the square root of cosine squared is the absolute value of cosine theta. But the thing is that, again, what would happen if I do the calculation at the level of ds squared, then I would get cosine squared and cosine squared here, and they would cancel out like, readily and so on. It's just because I do the calculation a bit too late here. The bottom line is that what we get is essentially r d theta, okay, which is a traditional length element that people are used to when they work on a circle, okay, and that the traditional polar, for example, coordinate system to characterize length on a circle and so on. Okay, so that's basically the idea on how you do it, etc. Now, to be honest, I think this is quite interesting for people to have a go at it. So, for example, and I'm not going to do it here, but if you try to apply the very same strategy we've done here, but then to a function f of x, y, which is equal to, so you've got y minus x squared is equal to 0. So essentially that's a parabola. And so you can try to find out what would be the inherited length element or metric on this particular curve embedded in R2, endowed with the Euclidean metric. Okay, so basically that's how that works, and we are going to see later on that these kind of things matter and do bring tons of different results that sometimes don't make sense if we don't know these things in the first place.